right, let's get started. While you're having your delicious lunch, it is an honor for me to introduce Dr. Leila Farhadi. Dr. Farhadi is an associate professor from George Washington University. She received her bachelor's degree in civil engineering and her master's degree in civil and environmental engineering from Sharif University of Technology. And her doctoral degree from MIT in civil and environmental engineering with a focus on hydrology and water resources. Before Dr. Farhadi joined George Washington University, she was a researcher at NASA Goddard Global Modeling and Assimilation Office, GMAO. Dr. Farhadi is the recipient of not one, but two very prestigious awards, the NASA Earth Science Division's New Early Career Investigator Award, as well as the NSF Career Award. Dr. Farhadi is passionate about education. She has engaged her undergraduate student in urban heat island measurement. And I just heard that she's got all her equipment ready and ready to get high school students start measuring, following SMAT protocols to do soil moisture measurement. So we are really delighted to have Leila here. In her talk today, she will tell us about how she derived evapotranspiration and water recharge flux, as well as the coupling between water and energy balance in the terrestrial water cycle, using novel data assimilation techniques that incorporate both ground and space-based observations. So I'm going to let Leila take it away.
Thank you very much, Amy. It's an honor to be here. Thank you very much for the kind introduction. Good afternoon, everyone. So Amy basically went through the journey I took before I became an associate professor in civil and environmental engineering. But when I was preparing when I was going to prepare the presentation, I talked with Simon, and he mentioned that it would be good if I kind of explain a little bit about the journey I took in order and what basically motivated me to become a water resource engineer. So I did some soul searching, and it was interesting for me as well. But I want to say that I became interested in water resource engineering impacted by the water crisis of the region I grew up in. So I was basically born in US, but I moved to Iran. I got my degrees, up to master's degrees in Iran. And I have to say, yes, everybody knows, most of the people here at least know that Middle East is warming twice as the global average, and the impacts of this include soaring heat waves across the region, declining precipitation, extended droughts, more intense sandstorms, and flooding. For example, as a student, maybe 20 years ago, 15 years ago, there was not many sandstorms happening in Iran, and now frequently we hear in news sandstorm impacting the air quality of different cities, something I didn't experience even as a 20-year-old. Flash floods is something else that is happening more significantly, more intensely across the region. So we have long periods of drought with flash floods, killing people and impacting infrastructure. There are parts of Iran, like southern parts of Iran, that are experiencing very high temperatures, and in the next 2 decades, they will become uninhabitable. Because of the water scarcity, there is a lot of usage of aquifers, such that 85% of the aquifers have been lost in the last 40 years, and 98% of the land is prone to land subsidence. And obviously, when water is scarce, there is going to be transboundary water disputes. Something I found maybe relevant to the students here is that my interest in water resource engineering started when I joined a student group as an undergrad, where we formed a student group visiting different parts of Iran's nature. Iran has a very diverse nature. It's in size of Alaska, but we could take a bus, go to different climate regions. And what I experienced, and then during the time I was a student, there was a lot of building of dams across the nation, trying to avoid or kind of be prepared for that water issues. So I became interested in problem-solving environmental issues, as well as now that I look back and hear about all these news of the impacts that have happened less than even 20 years ago, I have a better feeling of the impact of climate change. I want to specifically talk about two environmental issues facing the country. This is Lake Oromia. It's the largest wetland, as was one of the biggest saltwater lakes in the world. This is how the lake looked like in 1998, around year 2000, when I visited there with our student group. And it was a haven for different birds. It was a very lively environment. And actually, the reason we visited that was that we visited a lot of dams that were along the rivers feeding that particular saltwater lake. And eventually, both the impact of drought, the impact of poor water management, and these dams dried the lake in less than 2 decades. Like, this is by the time I got my PhD and I was starting working, this is how the lake looks like now, and it has caused a big, significant environmental issue. Now we are spending a lot of money, they're spending a lot of money trying to revive the lake. So again, pollution, growth, drought, and mismanagement. Another symbolic environmental issue is the Zayanda route. It's called Life-Giving River in Persian, and it used to flow year-long. This is how it looks when I was a kid. That's how it looks when I was a student there, an undergrad student. This is how it looks most of the time throughout the year. There's a lot of significant drought. And what you witnessed is not just unique to Middle East. It's not unique to the country I was raised, but its water crisis is a global issue. And it's anticipated by 2025 that 2/3 of the world population will live in water-stressed regions. And the issues that would arise as a result of that is water scarcity, drought, flash floods, ecosystem degradation, such as the one that we saw happen to Lake Oromia. And a lot of that, so it's going to be impacting the large portion of world population. How can we address that? Addressing the water crisis requires sustainable water resource planning and management. And by sustainable, because many of us know, that means that making sure that the water needs of our current generation is met, and we do not basically rob this natural resource from our future generation. Fundamental to sustainable water resource planning and management requires a deep understanding of how the water cycle works. And that's where my research lies. I'm interested in quantifying the different components of the water cycle and characterizing it, studying factors that impact the water cycle. And I will talk about this in a bit, but this information will help managers make informed decisions about how to allocate water, conduct infrastructure planning, manage watersheds, and climate change adaptations, and eventually ensuring sustainability of our water resources. So let's remind ourselves of what water cycle is, or what hydrological cycle is. Hydro, I guess, is the Greek word for water, so we can use these words interchangeably. So hydrological cycle is the movement of water on, below, and above our planet. It starts when sun heats the water of lakes, plants, the water that is in the soil, changing their phase into vapor phase, evaporating up, condensing, then precipitating back into the land. Some of that precipitation will infiltrate into the soil, be stored in form of soil moisture. Some of that moisture will travel deeper, feed our aquifers, and part of that precipitation will run off over land, feeding our rivers, going back. So it's basically, the water cycle is a combination of some stores, reservoirs that hold the water, and the fluxes of water that move water from one store to another. Now, these fluxes have different rates. Some are faster, some move faster, some move slower. For example, evapotranspiration, transformation of water from soil to atmosphere, is a fast process, but movement of water in our aquifers is a slow process. It's essential for life. One of the reasons that we have this life on our planet and in these various forms is because of the cycle of this fresh water providing this important resource to all different organisms. And without it, we would not be able to sustain life as we see it today. Now, when I talk about water cycle, we cannot study water cycle in isolation. It's not just one cycle performing by itself. As I was basically explained, the sun is the main driver of the water cycle. So the energy cycle is linked to the water cycle. And moreover, carbon cycle, nitrogen cycle, other terrestrial cycles, they're all linked and interact with each other and they work together. So a deep understanding of the water cycle is not possible without understanding the interconnections between these different cycles. If I want to explain that very schematically using a simple schematic diagram, let's assume that this shows our water balance equation. We have precipitation. Part of that precipitation will become in form of evapotranspiration, evapotranspirate back, part of it becomes runoff, and then part of it becomes recharge. Energy from the sun heats the earth in form of net radiation, so that's the total energy that the earth received. Part of it would be used to heat the ground in form of ground heat flux. Part of it would be used to, part of that total energy will be used to heat the air, which is called sensible heat flux. But part of that energy is the energy that is required to transform water from liquid phase into vapor phase, which is called latent heat. And latent heat is directly linked to evapotranspiration. Basically, they're the same thing. Evapotranspiration is the latent heat divided by the density of the water and the latent heat of the water molecules. Similarly, vegetation dynamics, which is a component of the carbon cycle, is linked to all of these. When plants transpire water, the stomata of the plant opens up and carbon is absorbed into to the vegetation in form of and then produces biomass through photosynthesis. So photosynthesis is also linked to evapotranspiration. So we can see that these cycles are working together. This means any change in any of the balance of any of these cycles will have an impact on the other. Any change in the energy balance will impact the water cycle. Any change in the land use would impact the water cycle. So we need to consider that when we are studying a water cycle. So going back to importance of quantifying and characterizing for a water cycle for sustainable water management, what are the ways that we could use to quantify and characterize water cycle? One of them is modeling, basically analytically understanding how water cycle works, similar to what I just mentioned. After we have this understanding, we would write the equations, we would model the system, and then have some estimates. The other way is through measurements. And then the last way I would kind of summarize it into three categories is to combine the models with the measurements to provide a better perspective. I want to first talk about modeling. How do we do modeling? Well, we can use all our analytical understanding, like our simple physical equations that we know from high school, laws of conservation equation of mass and energy. Any conservative quantity, either mass or energy, is conserved. So, for example, if we have a control volume, our control volume could be a piece of land, a farm, or it could be part of a watershed. If you have a control volume, the rate of change of this conservative quantity, which is water, carbon, or energy coming into the control volume minus the rate of the flux that leaves the control volume is equal to the change of storage of that quantity within that control volume. So this is the basic laws of physics that we could use to quantify water cycle. If I apply the same concept to the water cycle, energy cycle, and vegetation dynamic, as I explained, if I formulate them, and then even for each of these fluxes, if we write the parametric form, delve deeper, write the parametric form of the equation, eventually we will come up with a set of equations, and if we solve them, we would have a good understanding of, we can quantify a water cycle mathematically. And for us to be able to do that, we have to have some input variables to the system, like atmospheric data, precipitation data, forcing data, and then we have to identify a set of parameters. Once they are identified, we could run these codes, run the models, and then make estimates of different fluxes and states of the water cycle along with other terrestrial cycles. Then there are some shortcomings, obviously, to the modeling. Their accuracy depends on how we identify the input variables or atmospheric variables to the system. The accuracy depends on the parameters that we selected to the system. If they're not accurate, our estimates will not be accurate. And then the way we have modeled the system, our model structure. Okay. The other way is field site measurements, actually going to the field site and conducting measurements of different fluxes. For example, we could measure the amount of discharge in rivers, use rain gauge to calculate precipitation, soil moisture sensors to measure soil moisture, use lysimeters to estimate and measure recharge, use eddy covariance towers to estimate evapotranspiration. There are shortcomings associated with them as well. They're expensive. For example, at an eddy flux tower, I was trying to see the price. It cost about $50K like in 2013, which I was trying to purchase one. So it's expensive, and because it's expensive, it's not available everywhere. So there are just very limited number of field sites available. It's time-consuming, labor-intensive, and most importantly, they provide us with data at point scale. For example, how much evapotranspiration I have in here. So when we are doing large climate studies or large regional studies, their data are not, they're associated with a lot of uncertainty and inaccuracy. Another way to gain information about our water cycle is through remote sensing. Now, there are various ways of remote sensing. I specifically want to talk about satellite remote sensing. So there are sensors on top of satellites that measure the surface, measure the energy that is reflected back from the Earth. Now, this energy could the source of this energy could be the energy of the sun. So they measure how much of that energy is reflected back from the Earth, or it could be active sensors which they emit energy and then they measure how much energy was reflected back. And then based on the wavelengths and the amount of reflected back of energies, they can identify different characteristics of the land, and then they can transfer that information to information that we need for us to understand water cycle and energy cycle. So for example, this is SMAP, soil moisture active massive mission, that they have provided with information about soil moisture, and this LST, land surface temperature, we can have information about vegetation index. The shortcoming is that sensors do not measure fluxes, they can measure state. They cannot measure how much evapotranspiration you have or the movement of fluxes. This data is freely available, so that's the good thing. There's public available. You can download it for any different region and you can get that information. The good thing about the remote sensing data is the spatial scale. They come with different spatial and temporal scales, so they're really valuable data. The other method that I'm interested in and my work is called data fusion, data assimilation, combining modeling with measurements, where we say, okay, physical models will provide us with some valuable information. We accept that they're not accurate, they're not very good. Then observation will provide us with some information. How can we combine them to get a better perspective, better understanding of our water cycle? And with that, I will explain the NASA project that was kindly funded by NASA, and I got to work on this with my students. It's coupled estimation of evapotranspiration and recharge from remotely sensed land surface moisture and temperature. So very quickly, if I want to explain, we're focused on estimating evapotranspiration, which is the flux of water coming from the land into the atmosphere, and recharge, which is the flux of water after the water infiltrates into the soil. It if it continues its process and then starts feeding our aquifers. So these are two important fluxes of water cycle. Evapotranspiration, as I explained, links water, energy, and biochemical cycles together. So having an understanding, quantifying evapotranspiration would provide us with good information of how these are linked together, if one is changed, how it's going to impact the other, and etc. Evapotranspiration, quantifying evapotranspiration, provide us with valuable information about the water needs of a vegetation so we can produce better management plans for crop productivity, ecosystem health. We can better understand climate through estimation of evapotranspiration. And recharge is a very important flux if we want to sustainably manage our aquifers. Especially in water-scarce regions, once you're extracting water from the wells, you want to make sure that you don't deplete the aquifers over a period of time. And that's the knowledge of rate at which water is going to be recharged into the aquifers becomes really important. So our goal in this project was to develop an observation-driven or data assimilation approach, again, combining models with data to estimate important parameters of the evapotranspiration and recharge flux, so we can model them using information, hidden information in sequence of land surface temperature and moisture data. So I'll explain that in a bit, but there were some characteristics we wanted our approach to have to ensure its applicability to any part of the world. The reason we wanted to this approach is that land surface moisture and temperature data are available through NASA remote sensing data, and then modeling work can be applied to any scale, and then once we combine them, we can get a better estimate of these fluxes. So we wanted our methods specifically to be free of the need for requiring information about fluxes. I'll explain that in a bit, but here just a snapshot of what we did. We developed a coupled water and energy balance model coupled through the flux of evapotranspiration. Soil moisture data, as I said, when you look at a pixel, soil moisture itself does not have information about fluxes. But if you look at how it changes over time, it has some hidden information about how precipitation is divided into evapotranspiration, infiltration, and recharge. Similarly, if you look at land surface temperature, if you look at the time series of land surface temperature, it does have some information about how total energy from the sun is divided between latent heat flux and sensible heat flux. So we developed this method of estimation, which I will explain in a bit. It's called variational approach. So we observe soil moisture and land surface temperature. We developed this model that physical coupled model. And what we did is that we identified the unknown parameters that need to be estimated if we want to have a good estimate of evapotranspiration and recharge. And for a period of 1 month, the number of unknown parameters were 94 parameters. So the method we developed looks at, let's say, a period of 1 month. They look at observation of soil moisture and soil temperature. And it tries to estimate the parameters by making sure that our model estimates matches the observation as much as possible. It's called variational approach. It estimates 94 parameters, and there is an issue that how can we ensure that these parameters are estimated correctly? Maybe a combination of them are giving us a good result, but individually they're not. So for that, we develop an uncertainty quantification framework where we look at the uncertainty of the parameters, the correlation between the parameters, trying to identify the best possible set of parameters that would provide us with good estimates of evapotranspiration and recharge. So we did that. I thought I didn't want to go through the equations here, but if somebody is interested, there are references to the technique and the journal papers I have put here, and the references are at the end as well. But let's see how it worked. We selected a study region. Once we develop an approach, we want to test it to see if it's working. We selected Southern Great Plains for several reasons. First of all, it's part of Southern Great Plains is heavily instrumented, so it provides us with good measurements, good way of validation of technique, good way that we could quality check our technique. And it's also, we looked at part of Oklahoma Panda region. This region, drought is very common, and the aquifer underlying the Oklahoma Panda region is called Ogallala Aquifer that provides 97% of water in this region. So we want to make sure that we don't overuse the water, similar, so that so having a good estimate of recharge becomes really important. So the data used, again, are from open source satellite data. We used, we input some data to the model, usually mostly atmospheric data. And we also, for validation and quality check, we looked at the flux towers in that region to see what we estimate of our fluxes if it match what they have measured in that specific site. These are some of the results. I'm showing just snapshots of some of the results. These are maps of annual recharge and maps of annual evapotranspiration we derived for that particular region. These are, for example, our estimated value, and we looked at specific location where they had estimates of the range of recharge, and in all of these cases, our estimated value falls somewhere within that range, so it was a good call. And then we looked at evapotranspiration, for example, and look at different flux towers that were there. We applied our method, and then what we saw is that, for example, this green line here shows latent heat flux. And then the dots showed what is observed at the field site, and the lines show our estimates. For all of the components of heat flux, whether it's net radiation, whether it's sensibly heat flux, the blue ones, or whether it's latent heat flux at all these specific sites, our estimates match the measurements with a good degree of accuracy. So all in all, we can conclude that assimilation of land surface moisture and temperature into our physical model provide us with good estimate of fluxes. Now, can this method be applied to other regions? I said for testing our method, we applied it to Southern Great Plains. If I go back, again, I think I mentioned that throughout the presentation, but I want to specify the minimum data that is needed for method to operate. We need land surface observations obtained through satellites, and we need forcing data, which are satellite-based or atmospheric model-based reanalysis data that are available to the community. So that's the minimum data we need to conduct our estimation. But obviously, more data would provide us with more quality results, right? So if we have more data to quality check, not only the validation of our technique, but the satellite data that we input to our models, or the atmospheric inputs that data that we input to our models, we would get better results. So for improved results and quality check, we would like to see in situ surface observations to check the bias of our satellite observation. We would like to see in situ ancillary data. What is the land cover? It doesn't match what satellites measure or not. We would like to see in situ forcing data, precipitation, and etc. And we would like to have direct flux measurements whenever it's available to see how method is working for a specific region. Okay, so with that, I would like to mention how global community and protocols can help our project. Basically, the help could fall within this group for improved results and quality check. Atmospheric protocols I was looking at, there are several protocols that can provide us with valuable data about atmospheric variables that will be input to our model. So that would really helpful to check with in situ measurements. There are pedosphere soil protocols that we can use to get a better information, improve the quality of our estimation for different regions. There are biosphere protocols, land cover classification that would be really helpful for us to check the quality of the data that we input to our models. So in conclusion, quantifying and characterizing the water cycle is fundamental for sustainable water resource management. Satellite-based measurements of Earth's surface coupled models of terrestrial cycles. The more we put in the physics of the terrestrial cycles, obviously, probably we will have better information. Can provide us with some accurate estimates of fluxes, including evapotranspiration and recharge, and globe community can provide us with data that would improve the quality and accuracy of our model results at various regions. And these are the references, and with that, I thank you all very much, and with that, I will get any questions you may have.